Today we want to talk about percent composition. Percent composition, when we're dealing with compounds, we're first taking a compound like, for instance, HCl, and finding out the percentage of both elements in that compound, both the hydrogen and the chlorine in this case. Now remember that percent is equal to some part of a whole divided by that whole value times 100. So where are we going to come up with these values for the total of HCl and the part of H and Cl that are in that compound? Well, we're going to use molar masses for it, so we're going to use our periodic table. So the way that I ask you to do this is to write down the H and the Cl, and to write down the molar masses of each. Hydrogen is 1.01 grams per mole. And really on these problems, since it's percent and we're going to have partial over total grams per mole in each case, they're going to cancel anyway. So I tend to just leave those units out on this calculation since they're going to disappear at the end anyway. The chlorine is going to be 35.45 grams per mole. So that's hydrogen's part and chlorine's part. To get the total, then we're simply going to add it up. We end up with 36.46 grams per mole for our total value for the molar mass for this compound. So now in order to get that percent, I'm going to take each one of these parts, hydrogen for instance, divide it by the total, 36.46, and multiply by 100. That's going to give me a percentage. I'm going to do the same thing with chlorine. I'm going to divide by the 36.46 and multiply by 100. And when I do for hydrogen, I get 2.77% hydrogen, and I get 97.23% chlorine. That is my answer. I like that whole thing boxed. And then this is optional, but one thing that you can do just to double check on your answer is to add this up. If you've done it correctly, you should come out with 100%. Now, depending on rounding, you could come up with 99.99%, or you could come up with 100.01, but you shouldn't come up any further below or above than those values. So that'll just be a little double check for you. So let's do a little bit more complex problem. Let's look at aluminum sulfate. We're going to do the same thing that we did for hydrogen chloride for the one above. We're going to do what we've done in the past to get molar mass. We're going to take out how many of each of these elements we have. We have 2 aluminums in here. We have 3 sulfurs, and we have 12 oxygens. So when we multiply that by their molar mass, 26.98 for our aluminum, 3 times the 32.07 for chlorine, or for sulfur, excuse me, and 12 times our 16.00 for our oxygen. This gives us 53.96 for aluminum, 96.21 for sulfur, and 192.00 for our oxygen. Our total then, those are the partial values, the parts of each of those 3 elements in this total compound. And the total, when I add all of these up, is 342.17. A little bit of a shortcut. Instead of writing divided by 342.17 times 100 3 times, I'm just going to make one big division line to show that I'm going to divide each one of these values by 342.17, and then I'm going to multiply by 100. So what I end up with is 15.77% aluminum, 28.12% percent sulfur. I want these two places past the decimal. 56.11% oxygen. We've talked about before that I don't want to see molar mass, money, or percent in scientific notation. Those I want two places past the decimal. So that's how I want it reported. Once again, you can add this up, and if you add this up, you'll see that it comes out to be exactly 100.00 for our total percentage value, which it should. Okay, then what happens if we don't want to know every single element in the compound? What if, as in this case, we only want to know the CO2 present in this total compound? We're still going back to our equation that says percent is equal to our part over our total times 100. Now, in this case, the part that we're looking for is the CO2. And the total is going to be our NaHCO3. When we add up one carbon and two oxygens, we get 44.01 for CO2. For our NaHCO3, if we add up one sodium, one hydrogen, one carbon, and three oxygens, we get 84.01. grams per mole. Again, I'm leaving out the units. They're going to cancel in the end anyway. It's your one chance to leave out units in the middle of the problem. So we're going to multiply that by 100. And when we do, we come up with a percent value again. Remember, percent is not scientific notation. This comes out to be 52.39% CO2. So anytime you're asked for just part of a whole, that's how you're going to do it. The final type of problem that you're going to see is going to look like this. Asks us to find the number of grams of Fe and 25 grams of Fe2O3. So again, we're just looking for part of this whole. So we've got, first of all, before we can find out how much iron is in this compound, and it might be interesting to us for a variety of reasons. Maybe this is an ore that we're mining and we don't care about the oxygen. All we care about is the iron because that's what we're going to sell to make our money. So we want to know if it's going to be worthwhile or not for us to actually mine this ore. So we need to know how much iron we're going to get out of this much iron oxide. The first thing we need to know is what the percent of iron is in this compound. So we're going to go back up to our percent as partial over total times 100. And we want the percent of iron. Now be careful because iron in this compound is not just Fe. Iron in this compound is what? Fe2. Now we can do this one of two ways. We could put the 2 in front of the Fe. But I think right now, even though this isn't technically, you can't really write a formula for iron that says Fe2, this still lets us see that there are 2 Fe's in this compound. So I'm going to have you write it like this for now. Then on the bottom, we're going to have Fe2O3 for our total times 100. And if you add up 2 irons, iron is 55.85. If you add up 2 of those, you're going to get 111.70. If you add in on the bottom, if you add up the 2 irons and 3 oxygens, so you're adding in 3 more oxygens to this, we end up with 159.70. And we end up with a percentage of 69.94 for our percent of oxygen. Now it's tempting to box that because we got an answer, but that's not the answer it wants. It wants the grams of Fe and 2,500 grams of Fe2O3. Well, now we know that 69.94% of that 2,500 grams is iron. So we're back to just a basic percentage problem. We need to know 69.94% of 2,500 grams. And if you remember your percent rules on doing calculations with percent, we're going to change that value by multiplying by 100, move the decimal 2 places over, and when we plug in any percent value into a calculation, we always move that decimal, divide by 100, and we end up with 0.6994. This is a multiplication. So many rules and so many different teachers teach it different ways, but mine always said if there was an of in it, it meant you multiplied. So we're going to multiply by the 2,500 grams. And when we get our answer, notice that 2,500 gram that our units are going to be grams for this value. Is this going to be a two-place past the decimal value? No, it's not. Grams per mole, percent, and money are our two places past the decimal. Everything else is USS, units, sig fig, scientific notation. So when I work this out, I end up to 2 sig figs because there are 2 sig figs in this value right here. To 2 sig figs, I end up with 1.7 times 10 to the third grams of Fe. And that's the amount of iron in 2,500 grams of iron 3 oxide.